introduced delta K constant sequences. In this video, we'll discuss them in further detail and some properties of delta K constant sequences, along with some examples. The delta zero constant sequences are themselves constant. So a closed formula, here let me write it what it looks like. So a closed formula for them is easy to compute. It's just the constant. The delta 1 constant sequences are arithmetic, and we have a method for finding closed formulas for them as well. Every delta squared constant sequence is the sum of an arithmetic sequence, so we can find formulas for these as well. But notice that the format of the closed formula for delta squared constant sequence is always quadratic. For example, the square numbers are delta squared constant with closed formula an equals n squared. The triangular numbers, also delta squared constant, have a closed formula an equals n times n plus 1 all over 2, which when multiplied out gives you an n squared as well. It appears that every time we increase the complexity of the sequence, that is, increase the number of differences before we get constants, we also increase the degree of the polynomial used for the closed formula. We go from constant to linear to quadratic. The sequence of differences between terms tells us something about the rate of growth of the sequence. If a sequence is growing at a constant rate, then the formula for the sequence will be linear. If the sequence is growing at a rate which itself is growing at a constant rate, then the formula is quadratic. You've seen this elsewhere. If a function has a constant second derivative, then the function must be quadratic. This actually works in general. The closed formula for a sequence will be a degree k polynomial if and only if the sequence is delta k constant, meaning that the k sequence of differences is constant. So this tells us that the sequence of numbers of squares on a chessboard, which is 1, 5, 14, 30, 55, which we saw to be delta 3 constant, will have a cubic degree 3 polynomial for its closed formula. Now, once we know what format the closed formula for a sequence will take, it's much easier to actually find the closed formula. In the case that the closed formula is a degree k polynomial, we just need k plus 1 data points to fit the polynomial to the data. So let's solve the chessboard problem once and for all. We're going to find the closed formula for the number of squares on an n by n chessboard. Okay, so we've seen the sequence 1, 5, 14, 30, 55 is delta 3, delta cubed constant. So we're looking for a degree 3 polynomial, meaning that an is going to be some an cubed plus bn squared plus cn plus d. We can find d if we know what a0 is. Working backwards from the third differences, we find that a0 equals 0. Unsurprisingly, since there are no squares on a 0 by 0 chessboard. Thus, d equals 0. Okay, so now let's plug in n equals 1, n equals 2, n equals 3, and we get 3 equations here. First, 1 is equal to a plus b plus c, and then we have 5 equals 8a plus 4b plus 2c, and then I need one more row here, and then 14 equals 27a plus 9b plus 3c. I try to draw it in a little bit of a block. We can solve the system of equations to get a equals 1/3, b equals 1/2, and c equals 1/6. Therefore, the number of squares of an n by n chessboard is an equals 1/3 n cubed plus 1/2 n squared plus 1/6 n plus 0. And by the way, we can simplify this. This is actually just 1/6 times n plus 1 times 2n plus 1. And that's that. Now, real quick, when I got these three constants right here, I solved a system of linear equations with three unknowns. If you don't know how to do that, and that was a little confusing to you in this proof, that's actually perfectly reasonable. You probably wouldn't see some curveball like that on any given test if you're in a college discrete math course. So don't worry about that. In most instances, you'll only have at most two unknowns to solve for. And so you might be solving for quadratics, but this is the point of doing this problem is so that you get a little bit more of a complex taste in the real face in person. It's not really in person, online lecture, so that when you do the homework, the assignments, you'll get problems that are much more reasonable, and you'll be well prepared for them if you're prepared for this. So yeah, don't worry about it. Don't worry about how to solve these systems of linear equations. If you've taken linear algebra, I definitely expect you to be able to solve that. So anyways, thanks everyone, and I'll see you in the next lecture.